Now let's talk about another statistic which is also used for the same reasons, for the same purposes, for estimating a linear relationship between x and y, which is called correlation. Well, first of all, why we need correlation if you already have covariance, right? The problem with covariance is that it depends on the units. You remember that covariance is when you take a sum of x minus mx, right, times y minus my, okay? So this is the value in units of x, and this is the value in units of y. So for example, if x is centimeters and y is meters, so the covariance will be centimeters times meters, right? So it depends on the units. And the point is, if you change the units, you don't change the data, right? You just divide it to a constant or multiply it to a constant, but you change the covariance. And this is the plots that demonstrate this problem. So you can see this is a height of person in centimeters, right? So you can see the numbers. And this is the height of persons in meters. So you can see that the values are the same, it's just the different units, it's meters. And here we have weight, and here we have weight in kilograms, okay? You can see that the points look absolutely identical because we didn't change anything. The relationship is still the same. But you can see that this covariance is 100 times larger than this covariance, okay? And that's a problem because it means that we cannot use covariance to compare the relationship, especially if we are talking about variables with different units, okay? What to do? We need to improve the covariance a little so we can use it for comparison as well. And how to improve it? Apparently, we need to get rid of units, okay? And this improved covariance, it's actually called the correlation. So the correlation is when you take a covariance and then you divide to the standard deviation of x, standard deviation of y. So for example, if you have x is centimeters, y is kilograms, you have centimeters times kilograms in the top, and then standard deviation will be centimeters times kilogram in the bottom. So you get rid of units, and actually I can show it mathematically also, but I'll skip this part. You can prove that if you use correlation, if you standardize covariance by dividing to standard deviation of x, standard deviation of y, you also limit the values for the correlation. Okay. Now let's look at the same plots as I showed you before, but now I use a correlation, the calculated correlation coefficients as the title of the plots. So you can see that the correlation for height and weight is 0.96. It's pretty close to 1. Here we have 0.88, also quite large number. And you can see that it's a bit smaller than the previous one. So that's why we call it the weaker trend, right? Indeed, the correlation shows it to us, okay? This one, look, you have negative correlation and it's also not very, absolute value is smaller, right? So weak correlation and it's negative. Then finally here we have almost zero number, so we have no correlation, okay? How to interpret the correlation values? Well, the idea is following. If it's +1, it means that all points align exactly on a straight line. If they are a little bit scattered around this line, it's not +1 but very close to the +1, for example 0.99 or 98, and in this case we are talking about strong positive correlation. Okay. If it's -1, the points are also lying exactly on a straight line, but the slope of the line is negative. So for example, if points align on this line, it will be negative correlation. If points align on this line, it will be positive correlation. And it doesn't matter which slope the line has. The only important thing is that the slope is not 0. Okay. And then if you have 0, if you have no correlation, that's the case where the slope is 0 actually. It means that you don't have a covariance. So there is no relationship, at least no linear relationship between x and y. Okay. Then if you calculate correlation this way, it's called also the official name for these statistics is Pearson correlation coefficient. And actually, you can calculate correlation coefficient using also a couple of other formulas, which we are not going to talk about in this video, at least. Okay. So, how to say strong or not strong correlation? There are different rules, and this highly depends on what kind of data you work with. This is just a simple example of a simple table how to assess the correlation coefficient. So, if it's, for example, between 0 and 9 or above, it's very strong correlation. This is strong correlation. This is moderate correlation, and so on. But once again, this table is not something a rule of thumb. So this is correlation. This is how to estimate the relationship between two variables x and y using unitless statistics, which is correlation. And you remember, correlation tells you about two things: how strong the relationship is. How strong is it? And what's the direction of the relationship? Is it positive or negative? So sign of the relationship, right? It doesn't tell you, for example, something about the slope of line that follows the relationship, that fits the relationship, right?